welcome after the break. In this lecture, we are going to discuss about multispectral scanner and imaging devices. So far, we have discussed different kind of platforms. Briefly, we have also touched different kind of multispectral scanners associated or on board of different satellites. And now we will be further discussing about these multispectral scanners. Someone may have a question in mind that why we are discussing old scanners which are no more in space. For example, Landsat MSS, it was in 1972, worked up to 1976, and it is no more in space. So, why we are discussing? Similarly, maybe IRS list 1 and list 2. So, it is a very genuine question, but as you know that since then that data was being recorded or has been recorded since then, and that is what is most important, that now we are having more than 40 years of archives, having data from different sensors on board of different kind of satellites, and this archival data is becoming very useful, especially for change detection studies and studies associated with the climate change and other things. That means you are having 40 years of satellite based unbiased recordings of the things, recordings of the earth, a surface of the earth, and whether it is a forest or whether it is a water bodies or whether it is a bare soils or land, everything was being recorded since 1972 onward. And a very important product which is also available, very useful product. If one would like to see an area between 1972 to recent, then Google Earth provides that archive also. So, without downloading anything, just going in the history or archive, you can bring the cursor at the end in that menu, and you get the oldest image of that area. Probably most, if you are lucky, you will get an oldest image of even 1972. And since then, various images of all parts of the world are available, also for India. So, that is why it is important even today to discuss about the old sensors which are no more on the satellite. Those satellites are also not in service, those sensors are not working now, but their data is available, and data is by the by the time it is becoming more useful to study climate change and change detection studies, land use change, some geological changes in neotectonic studies and other things, landslide movements. So, in various types of studies, such old data is becoming useful, and therefore, their sensors should also be discussed and understood, the best part of those sensors and limitations also. Now, specific to this particular discussion, different types of sensors are there, have been there on different kind of satellites. So, we start with this kind of genealogy, that the sensor is there, and there are two basic categories which we can divide these sensors. One is passive, which is very common, another one is active, which is microwave sensors. Now, in passive we can divide in other two main categories. One is non-scanning, another one is scanning. Non-scanning means they can take data or acquire data in little different way, especially like imaging camera. So, they provide the data in form of a snapshot, like when we take a digital photograph using a DSLR handheld camera or even a mobile camera. So, we take a snapshot, not scanned images, which are more useful for scientific study. Using these cameras, we can acquire monochrome images, we can have natural colors. These were common when we had the film system. Now, we are having these digital systems, so we can acquire, of course, on the visible part, but infrared also. Our mobile cameras are sensitive to infrared lights as well, and very useful for night vision or night time photography also. So, even in a very dark condition, these mobile cameras can acquire images or photograph. Anyway, so we continue on this, that passive passive remote sensing can have two, non-scanning and scanning. Among non-scanning, again you can have non-imaging and imaging. So, non-imaging like microwave radiometer, magneto sensor, gravimeter, Fourier spectrometer and others. So, different kind of sensors are there. Those who work in the field of geophysics, they know about this magnetometer or gravimeter also, or microwave radiometer, but microwave radiometer in passive category. And there used to be satellite on Nimbus, a series of satellites on the sensor SSMI and SMMR, which were working in passive microwave part of EM spectrum, which is different than active. When we go for active again, so again you can have a scanning and non-scanning type, and within scanning you are having imaging, that object plane scanning and image plane scanning. These are so real aperture radar and synthetic aperture radar. So, most common active microwave remote sensing on different platforms, like if I give the example of Sentinel or NVSat, they are on the synthetic aperture radar. And synthetic aperture radar means that the size of the radar is not as big on board of the satellite, but they are synthetically it was created. So, that is why it is called synthetic rather than real. Then you are also having non-imaging and non-imaging active non-scanning sensors like microwave radiometer. Again, microwave radiometer we have discussed in case of passive sensors, but there are microwave radiometers which also works in the active remote sensing. Then you are having altimeters, laser water depth meters, laser distance meters and many other such sensors are there. So, various sensors depending on the requirements are the satellites are also there. When we go for passive and scanning imaging, then image plane scanning, object plane scanning. So, in case of scanning here in the active, and you are also having the TV camera, solid scanner we also see, then optical mechanical scanner and microwave radio. Optical mechanical scanner is the common in your desktop scanner kind of systems. They are little different than what we are having in space, but concept wise or technology wise, they are in some way similar to the space based scanners. So, these are the different types of scanners which are on board of different satellites, have been or are there. As you know that remote sensing we have just discussed that can be divided in two broad categories. One is active remote sensing and another one is the passive remote sensing. What exactly is an active remote sensing means here? That the instrument itself sends the pulse or the signals towards the earth, and whatever the back scattering which reaches after the interacting, the energy which came through from the satellite towards the earth, when it interacted with the different objects which are present, and when it goes back it is again recorded by the same platform. And when this is done, then we get these radar images, very common radar images. I will be showing their example. So, when we send the pulse is sent here, the pulse is, strength is maximum at that time when it is dispatched towards the earth. It takes some time to travel, and then this is the back scattering, and then maybe back scattering again. So, this peak, these peaks are recorded by the sensor, as also shown here, that here 1, 2, 3. So, this is the first, second, third pulse, fourth pulse likewise, and in return vegetation which is at different distance from the sensor or platform is having reaching time would be different. In case of a house or building, the time is different here. It is, say, if I take everything in terms of seconds, second unit, then the unit is second, then it is reaching at 18 seconds. Of course, it is not in seconds, in milliseconds, but anyway, for example. So, it is reaching in 18 seconds, whereas the back scattering from a tree which is little far from compared to the building, it is reaching at 26 seconds. And this is how these peaks are recorded by these active microwave sensors. So, when you are having a series of such data sets, then an image of a microwave from microwave sensors can be created. Wave by wave, the data is pulse by pulse, the data is sent and recorded, and likewise the images are created. The important point here to mention needs for power to operate, because each sensor, each satellite which is having a active microwave sensor has to have power to send those signals or pulse towards the earth. And therefore, generally the life of such active remote sensing platforms is relatively less as compared to passive remote sensing, because passive remote sensing, it does not have to send any energy towards the earth. The energy is coming from the sun which is here. But in case of active, the energy has to come from the sensor itself and will go back there. Here the energy is coming, it is illuminating the part of the earth, or maybe the emission which is coming out of surface of the earth and which is being recorded by the satellite itself. So, in passive microwave or in passive remote sensing, the source may be the surface emission or maybe cosmic background, sometimes maybe minute rain emission, but mainly in daytime you are having the sun and sun reflection is there, and it of course it reaches there. So, what we record is, in case of surface emission, what we record is brightness, temperature. Now, where these sensors are located, this is very important, whether it is active sensors or passive sensors. So, and these two extreme ends, on the top we are having active sensors which are shown in red color, whereas in the bottom it is written as passive sensors which are shown in blue color, and the EM spectrum here, the part of EM spectrum is shown in the black and green color. So, we go one by one again, starting with the active sensors, that we are having laser fluorescent sensors, and not very common. Emission measurements are in between this 430 to 750 nanometer. A typical excitation wavelength is 255 nanometer. This is here in this part of EM spectrum. When we go in the microwave region of EM spectrum, then we find lot of sensors. Here we do not have, in case of laser fluorescensors, we do not have this field is really coming up. We do not have regular satellites orbiting part of the earth. Through the shuttle missions or through the airborne, these sensors have been working or have been tested. But in case of when we come in the radar range, starting from 1 centimeter to 10 centimeter and more, and then we are having lot of bands within the radar range, starting K, X band, S band, L band, and of course very common is the C band also. So, all these and you are having SAR, that is synthetic aperture radar, or SLAR, that is side looking this aperture radar. So, both types of radars are there, or microwave radiometers are there, and they work on individual bands, generally either on C band or X band, which is very common with these. Of course, there are further divisions of K band, Ka and Ku are there. Certain missions were there and different bands, but the most common band currently either C, X or L. L band is also being used, which goes towards more radio waves kind of thing. It is also being used for some kind of transmission related with navigation satellites as well. So, microwave like your Sentinel or NVSat, they were using C band. C band means this much part of EM spectrum of microwave region is being used by NVSat or Sentinel satellites. When we come to passive sensors, Then we are having of course ultraviolet imagers, but spaceborne not possible, maybe drone borne or airborne is possible, but most common one in passive sensors is the visible part or near infrared, and it is quite broad compared to other windows which are available, and a lot of satellites of different countries of different types of sensors are working in visible and near infrared. Spectrometers are there, scanners are there, typical wavelength starting from 0.4 micrometer to 1.1 micrometer or 400 nanometer to 1100 nanometer. Then in between you do not have the atmospheric window, then you come to the thermal infrared, and here this region is 8 micrometer to 14 micrometer. This is the typical wavelength range for thermal infrared sensors. So, like Landsat MSS did not have, Landsat MSS was mainly focused in visible infrared, near infrared, whereas Landsat TM, which is thematic mapper, had these thermal channels as well, just single channel it had. NOAA AVHRR is having 2 channels in this thermal part of EM spectrum, which we have discussed in earlier lecture. So, different satellites again they are working in the different part of EM spectrum within different parts, like in thermal some are having single channel, quite broad channel, some are having 2 channels and maybe relatively thinner channels. So, likewise we are having active sensors operating in different part of EM spectrum, active sensors mainly in the radar part, whereas passive sensors mainly in the visible part and thermal infrared part. Microwave also, microwave, passive microwave, which I said that on Nimbus satellites SSMI and SSMR sensors were there, but they had very relatively very poor resolution of about 30 kilometer. Yes, 30 kilometer I am talking. So, 30 kilometer resolution, but the very valuable data, especially we use this data to drive snow depth over some part of Himalaya very successfully. But at 30 kilometer resolution, NOAA provides at 1 kilometer resolution, and now you are talking about centimeter resolution as well. So, all kinds of spatial resolution, remote sensing data, either active or passive is available. We continue on the passive sensors. That is for passive sensors, they do not have their own energy source. So, they depend on the source of energy either from sun or re-emittance or emittent thermal energy or thermal infrared, and these systems, that passive remote sensing systems measures energy that is naturally available, that is why they are called passive sensors, and these sensors can only use to detect energy when naturally occurring energy is available, and for reflected energy they need to have the sun which illuminates, and then only it will work. So, that is also there, and there is no reflected energy available from the sun at night, and that is why when I was discussing in NOAA AVHRR data, I said 5 channels will work in daytime, and thermal infrared channels can work both in daytime and nighttime. When it comes to nighttime, only 3 channels of NOAA AVHRR works, which are infrared, thermal infrared of 2 channels of thermal infrared. So, it of course, the sensors go because in visible channels, 2 channels which are devoted for visible part of EM spectrum, since you do not have the natural light source available, that is sun, therefore, these reflected channels will not work or will not have any recording. So, only you are having recordings in 3 channels in nighttime data. It is also possible to acquire nighttime data from Landsat new series like OLI or Landsat TM, because they are having 1 channel devoted for thermal infrared part of EM spectrum, but it is not normally available only on the request it has to be. So, if you start searching archives, you may not get nighttime thermal infrared data available from Landsat TM or ETM plus sensors. Now, energy that is naturally emitted by the earth for thermal sensors such as thermal infrared can be detected day and night. I said for NOVA AVHRR, and these two thermal channels also works in daytime and night time. In case of Landsat TM, ETM plus, again thermal channels also work, and same in the Aster also. So, the because in daytime this energy which is emitted, as long as the amount of energy is large enough to be recorded, and that is why relatively the spatial resolution of thermal channels on the same satellite is different. Of course, in case of NOVA AVHRR, the visible and infrared channel resolution is relatively anyway coarse, that is 1 kilometer. So, thermal channels are also having resolution of 1 kilometer, but in case of Landsat and TM, like normal channels will have 30 meter resolution, but your thermal channel can have 120 meter resolution. In case of OLI series, normal channels are having resolution of 15 meter, so thermal channel is having 60 meter, because you recall these 4 rules of remote sensing, and what it says that when you move towards the thermal part of EM spectrum, the energy available is very little for the sensors, and that is why as long as the amount of energy is large enough to be recorded, and in order to have sufficient energy for recordings, you have to cover a large area, and that means compromising on front of spatial resolution. So, that is why generally thermal infrared sensors are having coarser resolution compared to visible channels. These are different bands on the latest example from Landsat. Reflective bands are here, only reflective bands is there, not thermal infrared. Thermal infrared channels are there, and of course, we can assign different colors, additive colors for different bands as per our requirements, and can create a false color composite like this, or color combination like this is shown here. Now, we come to this false color composite. We have been using this word and discussing also, showing some images in false color composite. So, it is just right time now to discuss this, what is basically false color composite is. As you can see in this example, that I am having 3 channels, one is green, another one is red, and third one is near infrared. Compulsion of using near infrared is because you know when this spectral response curves, that vegetation is having maximum reflection in infrared channels or near infrared channels, and therefore, we need to keep that channel, so that we can, in color composite images, we can also have good information about the vegetation. Now, this is a infrared channel. So, if we assign green or red color, then it would be if we assign green or blue color, then it is going to be a little different scenario. So, generally what is done, as you can see here, though it is the red channel of visible part, but it has been assigned green color, and for infrared channel or near infrared channel, red color has been assigned, and for green color the blue has been assigned, because only available colors in additive color scheme are just 3: blue, green and red, BGR or RGB. Now, as you know that in additive color scheme, and this is how we have learned in very early stages of our schooling. And so, this color, though initially the green part of EM spectrum was represented in gray shades or in black and white panchromatic, now it has been assigned blue color. So, now it is visible in different shades of blue. Similarly, this red channel of EM visible part of EM spectrum is now assigned green color, and therefore, now we are seeing different shades of green. Similarly, the near infrared channel is assigned red color, and therefore, we are seeing in now red. So, when we combined these 3 channels or 3 bands, one is now blue, green and red through additive color scheme like this here, then we get a false color composite. Why false color? Because vegetation in the channel in which the vegetation has the higher reflectance, that means infrared channel, has been assigned red color, therefore vegetation is appearing red, and you know naturally vegetation should appear in shades of green. So, because in this combination it is not a true color, so we use the word false color. So, in standard false color composite images, the infrared channel is always assigned a red color, and therefore it becomes a false color composite. The advantage with this false color composite, as indicated earlier, that you get the vegetation coming very clearly out of this. But if you see the visible channels, the vegetation does not come very clearly here. So, because here it is high reflectance of vegetation in infrared, we have assigned red color, and therefore red is vegetation is appearing in red, in different shades of red, water body is appearing in blue, and some other bare grounds and other things, rooftop of some buildings are appearing in white. So, the discrimination of different objects in a color composite becomes easier if we go for false color composite composition. That is why we make false color composite. If we are having multiple channels, like in case of Landsat ETM plus or ETM even, then it is possible to see in near true color. True color images not available. So, what you see in Google Earth are not false color composites. You see near true color images, because if you fly on aircraft at 10 kilometer height and you look towards the ground, everything looks gray, brownish. It does not look very green like vegetation or water blue. No, does not appear like that. But when we see Google Earth images, we see vegetation as green, water bodies as blue. So, these are not really true color images, but they are near true color images are there. The main purpose here to combine these multispectral, that is multi-channels, and create this through additive color scheme a color composite. So, the main purpose is to discriminate different objects. Our interpretations of these images or analysis of these images becomes much easier. So, that is why these combinations, color combinations are used. One example here is from Nova Vecchiarad. In previous lectures also with different reference we have seen these two images. I am showing again, this is color composite and this is thermal infrared image of the same part, but it has been taken in the night time, but you can see here it is in the daytime. Of course, for the same day it also acquired daytime thermal infrared images also. So, they would that will look quite similar to what we are seeing is a 23 hours local time image of the same area. Now, about active sensors. Active sensors, as you know, they are having their own energy source for illumination, and these active sensors emits send pulse or signals towards the earth or target which they are focusing. And one important thing about active sensors and passive sensors I should not miss here is generally passive sensors are nadir looking sensors or vertically downward. So, these satellites are generally looking vertically downward, which we call as nadir viewing. Whereas active sensors, since they have to collect the back scattered data or back scattered signals, therefore, they are of nadir viewing, and this is what exactly also shown here, that they will look obliquely towards the part of the earth which they are scanning or recording the emittance. So, that or the back scattering, and that is very important to remember that passive sensors generally are nadir viewing, whereas active sensors are of nadir viewing or oblique in direction. Because the design is like this, that they send the signals and the same sensor or same spacecraft will collect later on and the same back scattered signal. So, for that purpose the design is like this, that they have to be of nadir. With the nadir viewing active sensor, it is not possible to collect the same signals, back scattered signals. So, advantages of the active sensors which includes the ability to you may obtain measurements anytime, because it is not depending on the sunlight for reflected light, nothing, because the sun it is having its own generator of light or energy. So, it therefore, it does not have to depend on. So, anytime the data can be acquired, but on normal spaceborne active sensors like Sentinel or NVSat or RadarSat or ERS or RISAT, they are having fixed time of orbit and they acquire the data. But if it is airborne, it is possible to acquire data anytime, regardless of time of the day or season. Season is important, whether it is a monsoon season or a winter season, whatever, because they are working in a large wavelength, and these large wavelengths can penetrate through the clouds. So, all this scattering and other things will not affect microwave part of EM spectrum. Therefore, they can acquire data at any time of the day or any season. That is biggest advantages with. So, like if somebody would like to use active remote sensing data for flood studies, then it is possible to use it, because clouds generally, when you are having floods, you are also having clouds. So, clouds will not hinder the signals, you will have a clean images, but in case of visible infrared and thermal infrared, the clouds will create a problem and images may not be very useful either. So, in such situations people resort for active sensors. Active sensors can be used to examining wavelength and that are not sufficiently provided by the sun, such as microwaves, or better control the way target is illuminated. Controls are there for to use different wavelengths of microwave region, and these active microwave systems require generation of fairly large amount of energy. That is why I said that whatever the source of, because after all they are having batteries and solar panels, and you cannot have too many batteries, otherwise the load will increase. So, there is always compromise, and the compromise with the time. So, the satellites do not last very long, active microwave, compared to normal passive satellites. And best example of active sensors is synthetic aperture radar, or in short we say SAR, ASAR, and WIFSARs and others are there. One of the examples, just I will go to first next slide and then come back again, just to give you a comparison. This is radar image taken by our own Indian RISAT satellite. 1, 2 will be launched soon, maybe end of this year or next year. And what I said, this is radar image for the same area, this is Google Earth image. See the difference, all fine details about the morphology, about the terrain, undulations, because vegetation is not creating much problem, because clouds and other things are not there, and therefore these structures, geological structures like fold and others can be seen very clearly here compared to what we see in the visible channels or near color composites. It is not very easy in relative to what we are seeing here, including it is very easy to see the water bodies in the microwave region, because this is completely absorbed, the microwave energy is completely absorbed by the water body, and therefore water body will generally appear black in microwave images, like here the example is shown. So, when somebody is working in an area for certain applications like in geological or structural mapping, or maybe for some civil engineering purposes, where one would like to have the complete or fair idea about the terrain conditions, and the terrain is not typical like high Himalayan conditions, undulations are there, hills and valleys are there, but not very rugged, then radar can work wonderfully well, as example shown here. That each little landforms, geomorphology, topography can be seen very clearly in radar images. Especially this example is shown of northeast India, that is Tripura, because generally otherwise these are, you are having lot of clouds regularly in these parts of the country. But as I have mentioned earlier, that radar images, there is no problem about the clouds, and therefore you get a very clear pictures. In case of visible channels, maybe after 20-30 orbits, you may get one day when the complete image is completely cloud free. But because of presence of vegetation or maybe presence of clouds, you do not get a very clear picture, as example I am showing here. Though relatively this image is quite high resolution image as compared to what you are seeing here. But the clear, because of it is working in microwave region and different rocks and located different places are behaving little differently with these microwave waves, and therefore you are getting a complete detailed image of that area. So, that is the biggest advantage with radar images. Okay, so now we are going to discuss about multispectral scanning systems, which are many types. What is the basically purpose of satellite remote sensors which acquire data using these scanning systems, which imply a sensor with a narrow field of view that sweeps over the terrain to produce an image. So, in that way it is a simple technique. I also gave example like a flatbed scanner also. So, there is a scanner is there, and when you put a paper from the below, it scans. Here in case of satellite borne scanners, it scans the terrain from the top. So, there are two main modes of scanning by which a multispectral images data can be acquired. One is across track scanning, or which is also called brisk boom, and the best example was Landsat. So, in that case, suppose the track is going like this, and then these scanners used to scan the part of the terrain or earth in a cross track across the track, and then later on some different type of scanners which is also called push boom scanners, and or along track scanners were also developed, which were on board of Spot and IKONOS satellites. So, first we will look at cross track scanning in detail. As you can see in the figure that this is the path of or orbit, direction of orbit from where the satellite is coming and going in this direction, and these scanners they scan line by line which is across the track. This is the height which is given here, and instantaneous field of view also is there, which we will be discussing in little detail later on, and that also decides the spatial resolution, and like in this example it is given 10 meter by 10 meter, and the swath is also given, he is about 20 kilometer. So, using a rotating or oscillating mirror which is inside a scanner, a cross track scanner, such systems can scan the terrain along scan lines that are right angles to the flight line. Flight line is here as mentioned. So, it is just perpendicular to that one, and this allows the scanner to repeatedly measure the energy from one side of the platform to other, and the data are collected within an arc below the system, which is typically of having about 90 degree to 120 degree. So, depending on the swath width and also depending on the resolution, because there is a relationship. So, this angle varies between 90 degree to 120 degree, and these in across track scanning, as you know, the incoming energy is separated into several spectral components that are sensed independently, because though these are across track scanning systems, but they are multispectral. So, therefore, in different channels or bands the data will be recorded, and when non-thermal wavelength component is directed from gratting through a prism or a diffraction grating that splits the energy into a continuum ultraviolet, visible and near infrared wavelength, and at the same time the dichroic grating disperses the thermal component of oncoming signal into a constituent wavelength. So, the same scanner will have two mechanisms, one for your visible and near infrared. Of course, ultraviolet does not reaches up to the space, and at the same time there is also a thermal scanning system or thermal data gathering system. So, in a cross track multispectrals are also possible. Similarly, in optical mechanical scanners, so within these cross track scanners there are little different options are also there. So, optomechanical scanners, again these are multispectral radiometers and which can record the image or data of part of the earth using a combination of platform motion and a rotating or oscillating mirror scanning, again perpendicular to the flight direction. So, here it is the flight direction or orbit direction, and these keeps moving, oscillating, and they detect in the since it is a multispectral scanner. So, in this particular schematic 4 channels are shown here. Other arrangements are almost same here. So, these optomechanical scanners are composed of an optical system, a spectrographic system, scanning system, detector system, and of course, reference system is also required. So, here as shown is the scan mirror, and it is a mechanical device. So, it is optomechanical. Prism is also shown here to have a different wavelength separated from white light. Multispectral scanner like on Landsat MSS that was on Landsat 1, thematic mapper also on later 4, 5 again on Landsat, and NOAA AVHRR, that is a advanced very high resolution radiometer, which are examples of optical mechanical scanners. And on NOAA AVHRR, these optomechanical scanners which are across track scanners are still continuing. So, they have been quite successful, but sometimes they also develop snacks and the problems arise, but so far in case of NOAA these have been working very nicely. So, opposite to across track scanner, we can also have along track scanner, and which are solid state and quite successful. So, as with the across track scanner, along track or push broom scanners record again multispectral images data along a swath beneath an aircraft as shown here, that this is the direction of flight or orbit, and this is the solid state which you are having. As satellite moves, line by line is scanned there. So, also it is similar to use the forward motion of the satellite to build up an image by recording successive scan lines that are oriented at right angles to the flight direction, and in that way though scanning is done in that direction, but this is all along the track and line by line is being scanned there, and since it is not optomechanical, a solid state thing, so things becomes much easier and robust. So, there is a of course distinct difference between along track and across track scanner systems in the manner that each scan line is recorded. In a long track system there is no scanning mirror, as we can see here solid state, instead a linear array of detectors as in the example of flatbed scanners. So, you are having an array of CCDs, charge coupled devices, and as that scanner moves, and the paper or whatever the photographs or drawings which is there is scanned. The same way, exactly same way it is what done through in space. So, the scanner you can assume it is in space and it is a scanning part of the earth. And each detector element, that is CCD in our case, is dedicated to sensing the energy in a single ground resolution cell along any given line. So, each CCD is focusing on individual pixels. So, if suppose the swath one image is having 2000 pixels, then that means the scanner is having 2000 CCDs in a array, and this is how it works very well. So, and what are the advantages of along track scanners over the cross track scanners? As that linear arrays, the CCDs arrays, provide opportunity for each detector to have a longer dwell time, so that they can sense the part of the earth equal to a pixel more efficiently, and they can stay over that for a longer time or residence time, over which to measure the energy from each ground resolution cell, from each pixel. And this along track scanners also enables a much stronger signal to be recorded compared to a cross track scanners, because the stay time or the scanning time is much more. There is a individual CCD is dedicated to individual pixels, and then you get a better quality image or high radiometric resolution image. Images are also possible with along track scanners. And also along track scanners leads to better spatial and radiometric resolution, as just mentioned, and also in addition to geometric integrity of linear array system is greater, because there is a fixed relationship among detector elements recording each scan line. Whereas in case of this Wishbone scanner or Postbroom scanner is that when they go on the edges, the mirror function becomes little different. So, therefore, there might be some problems with the data. So, here this example is also shown for a completely two-dimensional array, which is not exactly possible, but a scannering mirror is there, and then these linear mirrors are also there, and so on and so forth. Now, further advantages of along track scanners, that geometry along each scan line pixels in a row is similar to that characterizing an aerial mapping camera. And because CCDs are solid state microelectronic devices, and they are generally smaller in size and weight and require less power for their operation. So, that is from satellite operation point of view, it is another big advantages, because there is no moving devices, and if you are having a moving devices you have designed for 3-4 years, there will be wear and tear, because all the time those devices would be working. But if you are having a solid state, like in this case CCDs, then you require less power, less weight, smaller sizes, and that is again very advantageous. The one big disadvantage with the CCDs or the scanner system is to calibration, about the calibration of many more detectors. So, if there are say 10-24 detectors in an array, then their calibrations is very much required, otherwise there will be problems in the images, because each detector has to calibrate it equally, so that the responses is the same. So, this is one of the challenges associated with along track scanner. So, this brings to end of our discussion on various multispectral scanners, and also different types of remote sensing, active and passive, and various types of active and various types of passive remote sensing. Thank you very much.